So today let's start building up our table of transforms for different elementary functions. The idea is that once we would build the base tables of transforms, so this is the T domain and this is the S domain, and up to this point we have delta T 1 and then U of T 1 over S. The idea is that we're gonna build like a whole table of transforms, and once we do that, I mean, that will be a reference for us. So it will allow us to look up any function that we want, and then if we go from the left-hand side, from the left-hand side to the right-hand side, that's Laplace transform. And then if we go from the right-hand side to the left-hand side, that's the inverse Laplace transform. What we're trying to achieve is that when we encounter a problem with a circuit or a differential equation, we want to move everything to the Laplace domain through the Laplace transform, find the solution in the S domain, and then using the same table that we established for all those functions, we can go back to the time domain and find the solution in the time domain. Okay, so we want to establish that table. Up to this point, we said we know delta t and we know u of t. What else can we write the Laplace transform for? Well, using the properties of the Laplace transform that we provided as a definition, the first thing we could do is we can write the Laplace transform for any time-shifted signal. So, for example, ut minus t is going to be so how do we do ut minus, 3? We know that we can use the translation property number 3 of the defining properties of the Laplace transform. So u of t minus 3 transforms to, well, it should be the same as u of t, but it's multiplied by e. Remember, it's if I have f of t plus tau, that transforms to e of t plus lambda, that transforms to e lambda s f of s. So this is going to be lambda in this case is minus 3, so it's going to be e minus 3s. Right, so this is equal to e minus 3s over s. Okay, so we can directly write the Laplace transform of any translated signal. Another example, if we have, let's say, delta t plus 1, we translate the delta, right? That would translate to what? Well, I mean, the delta is 1, but this is shifted, so this needs to be multiplied by e1s, so this is going to be es. So this transforms this way. Okay, so we can transform the delta and the u and any time shifted version of them. Okay, what about if we do something else? What about having tu of t? How do we transform this? How do we find this transform using the properties and the transforms that we already know? Okay, so there are multiple approaches here, and they should, for things to be consistent, we should always get the same result regardless of what approach we use, right? So we could use skew symmetry, right? So remember that df by dt goes to sfs, right? So using skew symmetry, that tells me that d over ds of what? Of d over ds of 1 over s. Okay, let me actually write it simpler. Let me just say, hey, tu of t goes to 1 over s, right? Differentiate on the right hand side, right? So d over ds 1 over s, okay? And using skew symmetry, we know that df by dt gives me sfs. So using skew symmetry, d over ds of this, so it should give me the same thing times t, right? But now because it's skew symmetric, there's a negative sign here, right? So there should be a negative sign here. But I want to find the Laplace transform of t u of t. So I take the negative sign to the other side of the transform. I put it here. I can do that, right? I can multiply both sides by constants and I get nothing changes. So 2u of t goes to 2 over s. This is from the linearity of the Laplace transform, right? And then I can differentiate this with respect to s. I end up with t u of t transforms into minus, and then d 1 over s is just going to be minus minus, it goes away, and then 1 over s squared. Okay. So this is one way of finding it. So this is not the only way. We could find it by differentiation and should give us the same result. Okay, so what I can do is I can take t u of t. If I differentiate this will give me s f of s, where f of s is the Laplace transform of t u of t, right? That's what the act of differentiation does, right? I can write also f of s equals the Laplace transform of t u of t, right? If the fs is the Laplace transform of t u of t, then t u of t differentiated transforms to s f of s. Okay, all I need to do now is do this differentiation using the product rule. So I end up with t, and then differentiation of u of t is delta t, u prime is delta t, plus u of t times differentiation of t is t. Now using the shifting property of delta t, remember that when we integrate with delta t, f of t, we only care about the value of the function at t equals 0, or where the impulse is, where the Dirac delta function is. The value of the function doesn't matter anywhere else. So this is equal to f of 0, right? So because delta has this nature of it's 0 everywhere except at a single point where it's infinite. So the value of this function will not matter anywhere because delta t is 0 everywhere, but it will only matter at t equals 0. At t equals 0, this goes to 0 anyway. So this whole thing is 0. Right? So right? So I can so this goes to s f of s. So this tells me that u of t transforms to s f of s. But I already know what the transform of u of t is. I know that this transforms to 1 over s, right? So that means that s f of s equals 1 over s. So that means that f of s needs to be 1 over s squared, right? So the result we've obtained is clear. It's that Laplace transform of t u of t is 1 over s squared. Okay. So notice here I'm using this notation. I'm using this notation to do the Laplace transform. I could write this whole thing, do this whole manipulation using the alternate notation as follows. So I take L Laplace transform of t u of t. I'm just showing you how the notation is versatile. You can use any notation you want, that's fine. Prime, that equals S Laplace transform of u of t times t. I prefer to do it this way. I prefer to use the curly brackets, right? And then this equals Laplace transform of t delta t plus u of t right? This goes to 0 equals R's Laplace transform t u of t, and then Laplace transform u of t is just 1 over s equals s Laplace transform t u of t. So that tells me that the Laplace transform of t u of t equals 1 over s squared. The same result, I'm just writing it in the alternate notation. I mean, you can always jump back and forth between those two notations. Okay. Right. So now we know how to do t u of t. What about in general if we have t to the power n u of t? Sorry, excuse me. What's the Laplace transform for this? Right. So I mean, this is fine. If we differentiate this once, what happens? We end up with n tn minus 1 u of t, right, plus tn delta t. And again, we note that the same thing, using the shifting property, the value of this function only matters at t equals 0, which goes to 0. Right, so this would be the result. Now it's clear that if we repeat this n times, we will get n times minus 1, n minus 1 times n minus 2, and so forth. So we get from n minus 1, n minus 2, n minus 3 all multiplied together, right? So until we get, and we'll still have u of t. So if I take tn u of t and I differentiate this n times, I end up with n prime, and not n prime, n factorial. This is equal to n minus 1, n minus 2, all the way to 2, 1. Right? This is just the factorial function. Right? That happens naturally, occurs naturally when you differentiate repeatedly, times u of t. So here you can see here, every time we do a differentiation, we still end up with u of t. Okay, now we can take the Laplace transform of both sides. I can take the Laplace transform of this, and it equals the Laplace transform of this, right? So here I'm taking, this is equal to the Laplace transform of tn u of t, but this is differentiated n times. Each, in the Laplace domain, each differentiation is equivalent to multiplication by s. So this is s to the power n, because I do the differentiation n times, so I multiply by s n times. The Laplace transform is linear, so I can take the n factorial out. I end up with n factorial Laplace transform of u of t, which is 1 over s. So I end up with the Laplace transform of tn u of t equals n prime over s n plus 1. Written in alternate notation, tn u of t is a Laplace transform, anti-Laplace transform, inverse Laplace transform pair with n prime over Sn plus 1. Okay, so we're slowly expanding our repertoire. So now we can do u's and deltas that are shifted. We can do t to any power times u of t. Okay. All right. So also we can time shift this, right? So if I could have t minus a to the power n, then u t minus a. Oh, be careful here. If I shift the t here, that's underneath the power of n, I also need to shift the t and the u. When you shift it in time, you need to shift in time uniformly. So it should look like this. Shift, this is the shift by a, right? If there is no t minus a here, if I just do t minus a to power n ut, this is not time shifted by a, because u of t is not, the t inside the u of t is not also time shifted along with the function of t, right? So We know how to handle translation, right? It's the same thing. This transforms to the same thing n prime over s n plus 1, but then the time shift in the t domain is equivalent to e minus a s. So we multiply this by e minus a s. All right. What if you had shift in the time domain? Shift in the time domain, in the s domain. Shift in the s domain will look something like this. You would have e minus at t to the power n u of t, right? So this is equivalent to shifting something by in the s domain. So this is the same. We get the same thing, but now s is shifted by a, s plus a. Right? So you'll always have to go back and remember the properties, and this allows you to manipulate a lot of expression just from the properties, just directly from the properties. Okay. Okay, an interesting example. What if I have something like this? What if I have e minus at and then t minus b n u t minus b? What would this transform to? Well, first let's ignore this e minus at. This represents shift in the s domain, translation in the s domain. Let's take this by itself. This by itself would transform to n prime over s n plus 1, and then it's shifted by b, so this is will have minus e to minus bs. This is the transform of this thing by itself, but then it's multiplied by e minus at. So going back to the third property, this is equivalent to a shift in the s domain by a. So this is equivalent to s plus a, and then instead of s I have here s plus a, right? So what I'm trying to say is that the general properties that we discussed in the last lecture are extremely powerful, and if you know how to use them correctly, you can figure out how to do the transform for a wide range of different signals. Okay. For example, if I have this t minus 1, let's say I have t minus 1 squared u of t. Is this a time-shifted signal? No, it's not a time-shifted signal. Why? Because I don't have here ut minus 1. How would I try to find the Laplace transform of this? Well, I mean, there's no way here other than trying to evaluate this expression. So let's do that. So this is going to be t squared minus 2t plus 1, right? Square of the first term, square of the second term, 2 times the first term, second term, right? U of t, right? So this equals t squared u of t minus 2t u of t plus u of t. And here we can apply the linearity of the Laplace transform. So the Laplace transform can apply to every one of those terms, and we end up with t squared u of t. So this is going to be n factorial over s n plus 1. In this case, n is 2. So 2 factorial is going to be 2 over Sn plus 1, S3. So this is this first term, minus 2. Tu of t is going to be n factorial. 1 factorial is 1 over Sn plus 1, which is going to be s squared plus 1 over s. So this is what the Laplace transform would be, right? So I can write that the Laplace transform of t minus 1 squared u of t. Here I cannot apply the translation property right away because t is not translated along with the function. I had to evaluate the expression itself. So this transforms to 2 over s cubed minus 2 over s squared plus 1 over s. Okay? All right. So, I mean, we now know how to do like a bunch of different polynomial expressions. That's what that transformation gives us. Gives us the general transformation of t to the power n gives us the ability to transform different exponential functions. Let's not exponential, sorry, polynomial functions. Right now, let's talk about exponentials. And exponentials are easy; they just apply from the time translation, from the frequency translation property. So let's say I have EAT u of t. How do I transform this? So remember property 3. If I have e minus lambda t f of t, that transforms to fs plus lambda, well, same deal here. U of t transforms to 1 over s, but multiplied by e a t. This is e minus a t, right? So this is equivalent to a translation by minus a in the frequency domain. So this is going to be 1 over s minus a. Right? And this is how the exponential function transforms. And that's it. We found it directly from the defining properties. We can mix now Tn and EAT u of t. Right? We start with the transform of Tn Sn plus 1, but then this is equivalent to translation by multiplying it by e to the at is equivalent to translation in the s domain by minus a, so this becomes s minus a to the power n plus 1. Okay, so now we can do, our table is expanding. We can do delta u polynomials t squared all the way to tn. We can do time shifted versions of all those, right? And then we can do exponentials and tn times EAT, right? What's left out of the elementary functions? I mean, there are a lot of elementary functions, but the major elementary functions that are left are really the trigonometric functions. So now the question is, how do we transform sine omega t? And remember, we always need to multiply by u of t, or cosine omega t u of t. Right? So there are different ways of finding those transformations. What matters is that whatever way we use to find the transformation, it has to be consistent. I mean, we always should get to the same result, and we do typically. We do actually all the time, or else this wouldn't make sense. If you use a certain method to find the Laplace transform, and then you use another method and you get a different result, then the Laplace transform is not unique, which doesn't make sense. Does not follow the definition of the Laplace transform. So how would we do that? How would we do the sine and cosine? Well, let's start. There are multiple ways of doing that. One way is we could take the sine omega t and write it in terms of the exponential function. So this is equals to AE. What's sine omega t? It's equal to EJ omega t minus E minus J omega t over 1 over 2J. So this is from calculus, or I think we talked about this in the beginning of the course. You can write the sign as this way, right? And then we know how to do the Laplace transform for an exponential function, right? So the Laplace transform for this is linear, so it's going to be 1 over 2j. What's the oh, remember, of course, u of t. So there's always u of t. Right, so there's u of t here. So 1 over 2j, ej omega t u of t, that's 1 over s, but s has shifted by minus j omega t. So it's going to be minus j omega, sorry. Okay? And this is minus 1 over 2j. This is the same transfer function, Laplace transform for 1 over s, but shifted by plus j omega. Aha, so the Laplace transform will be this thing, but we can manipulate this thing, we can evaluate this thing, right? So I can do this. It's going to be equal to 1 over 2j, and then multiply this by s plus j omega over s plus j omega. So what would that give me? That would give me s squared minus j omega plus j omega is going to give me j times minus j is what? 1, right? It's going to give me omega squared, and then minus j omega plus j omega is going to be 0. So this is just going to give me s squared plus omega squared minus 1 over 2j, and then multiply the numerator and denominator by s minus j omega over s minus j omega plus s plus j omega. Same thing, it's going to give me s squared plus omega squared. All I have to do now is sum those two up. I end up with 2j s plus omega squared, and then in the numerator I'll have s plus j omega minus s plus j omega. S goes with s. J omega plus j omega is 2j omega. 2j cancels with 2j. I end up with the transform of sine omega t u of t being simply omega over s squared plus omega squared. Right? So this is one way of doing this. I could do this, find this transform in using another technique, and if everything makes sense, if everything is consistent, I should get the same result. Let me show you another technique. That's very useful. What we could do is we know that if we take the sine and we differentiate it twice, we get sine again. What happens if we differentiate it once? Well, we use the product rule. So I get, in this case, cosine omega t times omega u of t, right? Plus sine omega t delta t. I know that the property with shifting property of the delta, where it's 0 everywhere except at 0, so the sine only matters at 0, and at 0 the sine omega t is 0. So this expression does not matter anymore, right? But then I take this and find the second derivative of this. And I end up with differentiating this again. So I end up with cosine is minus sine. So I end up with minus omega squared sine omega t u of t, right? And then I'm using the product rule, plus omega cosine omega t delta t. Again, the value of this function only matters at t equals 0. Cosine omega t at t equals 0 is 1. So 1 times omega. So this whole expression goes to omega. Right? So d squared over dt squared over sine omega t u of t is equal to minus omega squared sine omega t u of t plus omega delta t. I can take the Laplace transform of both sides. I end up with, so I'm differentiating twice, so I end up with s squared, one s for each differentiation, Laplace transform of sine omega t u of t equals minus omega squared Laplace transform of sine omega t u of t plus, what's the Laplace transform of delta? 1, right? So it's going to be, take omega out, it's going to be omega times 1, so it's going to be omega. So we end up with this expression. I can take this to the other side. I end up with s squared plus omega squared times Laplace transform of sine omega t u of t equals omega. So I end up with the Laplace transform of sine omega t u of t equals omega over s squared plus omega squared. We got the exact same result, and we should get the exact same result. Right? Now, what about the cosine? Well, we can follow the exact same logic. We could either differentiate the cosine twice, or we could write cosine omega t as half e j omega t plus e minus j omega t. We can either write cosine as follows. So this is the first technique here that we did for the sine, or we could differentiate the cosine twice and do the calculation that way. All right. So let me actually do it the second way. Let me take cosine omega t u of t and differentiate it twice. What happens when I differentiate it twice? So differentiating it the first time, I end up with minus omega sine omega t u of t plus cosine omega t delta t prime. Right? I don't want to substitute the cosine because I still have to differentiate again. Right? So this, when I differentiate again, I end up with so I differentiate actually, let me do this. Yeah, no, it's fine. I mean, this is no. Let me keep this. It's fine. I'm gonna get the right result if I keep this. I'd always would rather just put in put 1 instead of cosine omega t at the end rather than at the beginning. Right? So if I differentiate this term, I end up with minus omega squared cosine omega t u of t, right? And then I'm using the product rule. So there I'm going to have minus omega sine omega t delta t, right? And then I'm differentiating this again using the product rule. So it's going to be it's going to be minus omega sine omega t delta t, right? And then plus cosine omega t delta prime t. By the way, what is the Laplace transform of delta prime t? This is easy, right? The Laplace transform of delta t is 1, right? So the Laplace transform of delta prime t is just the same as the original function times s. The differentiation in the s domain is equivalent to multiplication by s. So we take s, we take 1, we multiply it by s, and we end up with s. So delta prime t transforms to s. Delta double prime t transforms to s squared, and so on and so forth. Right? So now we can simplify the delta expressions. So here, this goes to 0, right? Because it's a delta function. This goes to 0 because it's a delta function. Delta prime, now it's trickier. But what matters is that the function is still, I mean, it's still the same thing. What matters is that the delta or delta prime only exists at where the impulse is, at where the Dirac delta function is. So this is going to be 1, right? And then what we could do now is we can take the Laplace transform of this. So what happens if we take the Laplace transform of this? So this is going to be Laplace transform of both sides. So if I take the Laplace transform of this is going to be, it's cosine omega t ut differentiated twice, so it's going to be s squared Laplace transform of cosine omega t u of t equals the Laplace transform of the left-hand side of the equation is going to equal to the Laplace transform of the right-hand side of the equation. So this is equals minus omega squared Laplace transform of cosine omega t u of t, which I'm trying to find, right? This we said is 0, 0, but I have delta here. So this is going to be, we said this is plus s. So I take this to the left hand side, I end up with s squared plus omega squared Laplace transform of cosine omega t u of t equals s. So the Laplace transform of cosine omega t u of t equals s over s squared plus omega squared. Okay, so we know now that the sine omega t u of t transforms to omega over s squared plus omega squared, and then cosine omega t u of t transforms to s over s squared plus omega squared. So now we included sines and cosines in our table. Okay. Now in second order systems and higher, and in circuits also, we discovered that important solutions occur that are not sine and cosine. So exponential functions occur that they are important. Sinusoidal solutions occur, they are important, but also a third kind of solution occurs regularly, which is the sinusoidal with an exponential envelope. So it's also important to find the Laplace transform of those kind of signals. And given what we know, I mean, those are easy, right? Exponential is just a shift in the frequency. So if I have a Laplace transform of e minus at sine omega t u of t, we know that that's equivalent to shifting s by a, right? So this is just equals omega over, instead of s plus a squared plus omega squared. Right? And then the Laplace transform of e minus at cosine omega t u of t. Again, here is just a matter of shifting s by a. So it's going to be s plus a over s plus a squared plus omega squared. Right? So we now know how to handle the Laplace transform of all the elementary signals for voltages and currents that are going to arise in circuits, and that we studied already. So we already built like a big table of transforms. Okay. Now, after we've done all this and constructed our table, I'm gonna give you the derivation for the integral formula for the Laplace transform, right? And then we can easily derive this formula, and in many textbooks you would see the Laplace transform. The starting point for the Laplace transform would be that integral formula, right? It doesn't have to be. We can always define it differently, as we did in the last lecture, right? The reason I don't like to start with the integral formula is that the integral formula is problematic a bit because it does not converge for all of S. It is you have to always be careful where it converges and where it doesn't. While starting with the properties, you don't have to worry about that. So let's derive the integral formula. The idea behind the integral formula is simple. The idea is we take any function, and remember we're dealing with functions that are multiplied by u of t, so the functions will be 0 in the left hand side for t less than 0, right? Then we'll have any general function. We can always approximate this function as a train of Dirac delta functions, right? So this would be like an approximation for this function. Each delta function, so this is like a train of delta functions, meaning those are delta functions that are shifted in time at every point in time, and they have different magnitudes, and their magnitudes are equivalent to the value of the function. So the magnitude or the weight of every Dirac delta function is going to be the value at that time t times dt. Okay, so those have infinitesimal weights, but that's fine. There are an infinite amount of them, so they do add up to something, right? So I mean, this follows from the ability of writing x of t as the integral from minus infinity to infinity of x of tau delta t minus tau d tau. This formula is self-evident from the shifting property of the Dirac delta function, meaning this Dirac delta function is zero everywhere except at t equals tau. This is shifted by tau, right? And sorry, here we're integrating with respect to tau. So this is shifted by so this is zero everywhere except at tau equals t, right? So what we get here is output is x of t, right? So this just follows from the shifting property, and this clearly shows us that we can decompose any signal as an infinite sum of impulses of Dirac delta functions, right? So this is the picture. Now the idea is that each one of those impulses or Dirac delta functions can be transformed easily. We already know how to transform each of those, right? T minus tau. We know how to transform this. This is a constant, by the way. So this is the value at a certain amount at a certain time times dt. This is infinitesimal, and we know how to transform this. So this transforms to what? This transforms to so what's the transform of delta? It's 1, but this shifted by tau, so we multiply it by e minus s tau. That's the translation property times the constant, which is x tau d tau. Okay, so this is the transformation of a single impulse or a single Dirac delta function. But from linearity, we know that the function is the sum of all those impulses. So the total Laplace transform will be the sum of all those results. So the Laplace transform of any signal, general x of t signal, any signal x of t in general is going to be this integral. It's going to be the sum of all of those. And because x is 0 for t less than 0, we're going to start at 0, go to infinity of x of tau e, let me do t, x of t e minus st dt. This is how we get the integral formula, right? So this is the formula that allows you to find the Laplace transform for any general signal. So we know how to find the Laplace transform for any elementary signal, but what if we have some random signal, right, that we don't know how to manipulate? We could opt to use this integral formula, and this integral formula naturally occurs from the properties, right? Many textbooks and in most treatments, people start with this formula. The problem is starting with this formula is that this formula does not converge. So in many cases, you have a Laplace transform, but the integral definition does not converge. It gives you infinity, so you have to use different tricks to try to kind of get it to converge. That's why I don't like starting with it. It's very simple. Instead, to start in a more axiomatic way by presenting some properties as axioms, and then getting the transforms from those properties, right? But you should be aware of this formula, right? And you probably, if you took a mathematics course, engineering mathematics, you probably encountered this formula along with Fourier transform. Okay. The Fourier transform is the same as this, but instead of s, we put in s equals j omega. See this curious substitution, s equals j omega, that we did previously in the previous chapter. It shows up again, and this gives us the Fourier transform. So up to this point, I'm talking about s as a parameter and t as a parameter, right? What I haven't discussed yet is that s, we shouldn't think of s as only in the real domain, on the real line. S could be complex. In the same way, t could be complex, but we only deal with real signals, so we limit ourselves to t being real, but s could be complex. And naturally, it's very natural to think of s as being complex, right? This arises from signals in the s domain having like denominators where you have s squared plus b s plus c. When you factor those out, those don't always give you real roots. They sometimes give you complex roots. That's why it's more natural to allow s to bleed into the complex plane. Okay, so yeah. So we will discuss this further. I think the only thing we need to discuss after this is the initial and final value theorems. And we could derive those theorems easily from the integral formulation of the Laplace transform. Let's see, let me do this quickly. I mean, those are not very hard theorems to prove. Let me demonstrate. Let me do that now. Okay, so yeah, so this is a representation, this is a derivation and a presentation of the final value and initial value theorems, two very important theorems in Laplace theory, and they allow us to using the Laplace transform of a signal, using that to determine what the final value of the signal is and what the initial value is. Why is the final value important? Well, the final value is whatever value, let's say whatever value the signal settles at. Let's say you're solving a circuit and you solve for the voltage. You use the Laplace transform technique. You can directly find what the steady state value of the voltage is going to be by using the final value theorem. So how would we derive and state those theorems? Well, right. So we start by taking a signal, general signal xt u of t, and differentiating it. So d here means d by dt. That's just the differentiation operator. We know that if I take the Laplace transform of differentiation of xt u of t, I end up with s x of s. Right? So this is the basic property of differentiation. And then I can apply this differentiation, right? So this is going to be x to t delta t plus x prime t u of t, using the shifting property of delta t, x of t. The only value of x of t that matters is x0. So instead of x of t, I can put x0. And then I take the Laplace transform of this sum. I use the linearity of the Laplace transform. I end up with x0 here because Laplace transform of delta is 1. And then I have the Laplace transform of x prime u of t. Right? But I know from the integral formula that the Laplace transform of x prime u of t is this integral, right? And now I have two paths I can go to. I can either examine what happens when s approaches 0, and this gives me the final value theorem, or I can explore what happens when s goes to infinity. Well, when s approaches 0, what happens? Well, here, when s approaches 0, e minus 0t is 1. So I end up with that integral of x prime t dt. So what is integration? Integration is just from integration here is just finding the antiderivative of x prime and evaluating it at infinity and 0. Well, the antiderivative of x prime is just x. So it's going to be x0 plus x prime plus x, which is the antiderivative of x prime, evaluated at infinity and 0. So x0 cancels with x0, and I end up with x infinity occurring when I take the limit as s approaches 0. So x infinity is the final value of the signal. So the final value is just the limit of sxs as s approaches 0. Let's take now the limit as s approaches infinity. So I'm taking limit s approaches infinity of sxs. Well, this is easy. S approaches infinity here, I get e minus infinity t, which is 0. So this whole term goes to 0. I end up with only x0. So I end up with x0, the initial value, equals this. So those are the two theorems, the final value theorem and the initial value theorem. The final value theorem allows us to get the final value, the steady state value, from the Laplace transform. So I just take sxs, take the limit as s approaches 0, that gives me the final value in the time domain. And then if I take ssx and take the limit as s approaches infinity, that gives me the initial value in the time domain. Okay, so with that, we're ready to apply the Laplace transform, the properties that we studied, this theorem, the table that we constructed in this lecture. We're ready to apply all that for solving differential equations, linear first order differential equations, and second and third order, no matter what the order is, and also solving circuits. And why do we want to solve circuits with the Laplace transform? It allows us to easily. So remember what we did? We started with DC analysis and then we went to AC analysis, right? The Laplace transform is going to allow us to solve for transients in general, right? So AC analysis was concerned with finding the AC steady state, right? And then for DC analysis, we just look at the DC response, and then we looked at the transient response for only specific step signals. Now with the Laplace transform, we can solve for any transient for any circuit, and we will show how to do that in the final two lectures. All right, thank you guys. We'll continue this next time.